work that Clara and Adam and I have been doing, and sort of a topic broadly that I looked at for my thesis, which is the link between two modes of variability in the tropics, the Madden-Julian oscillation and the Quasi-Biennial oscillation. And I want to recognize, in addition to my collaborators, as a grad student, I was funded by a NASA grant, an NESSF grant, and then my postdoc is funded by the NSF. And they funded a lot of work that I'll talk about today. And in addition to my own work with Clara and the work that we've been doing, particularly with the GISS model, I'm going to present sort of an overview of a lot of different people's work. So this is by no means just the Zane Martin show. There's a lot of people working on this topic. So I thought, because I at least have, it's a long time to sit in front of a computer screen. I thought I would just sort of get the story out of the way and then keep coming back to this slide. So if you lose focus or a child or a pet wanders in, hopefully this slide will help keep you grounded. So basically what I want to talk about today, right, is these two oscillations that are important in the tropics. They're called the MJO and the QBO. I know that a lot of you know one or both of them, and they're different in a lot of ways, and I'll talk about how. But the motivation for this talk really is that they are strongly connected, and that's a relatively recent finding, that there's this strong link between the MJO and the QBO. And it's served as a sort of springboard for a lot of scholarship since around 2016. And the problem that I am not going to answer, but I'm going to sort of give you a sense of, where is the science on this and what are we struggling with and where might we go, is that we don't really understand the physics of this MJO-QBO connection, and models, and I'm using that term relatively broadly here, can't capture the connection in the same way that it seems like it exists in the real world. So I'll talk about work that we have done, in particular at the end in the GISS model, to try to get at both the physics and where our model's struggling, give you a sense of what does work and what seems promising to move forward. So just to give some background really quick, I know this is a pretty savvy audience when it comes to climate things, but the Madden-Julian oscillation is a big player in the tropical troposphere. If you study tropical meteorology, you're bound to come across the MJO. And what it is, to first order, is it's a system, a large planetary scale system that couples convection and circulation. So this panel is a cartoon from NOAA, which shows a schematic of the MJO. So what you see, we're looking down on the tropics on large scales, and there's an area called the active phase of the MJO, where you get anomalous stormy wet conditions. You see increased cloudiness, storminess, precipitation, and that has a characteristic wind pattern that goes along with it that spans the depth of the troposphere. So we have convergence at low levels and then ascent, up to around 200 millibars with divergence at those upper levels. So in addition to that stormy active region, simultaneously to the east in this schematic is a sort of opposite mode where we have downward motion and anomalously sunny, dry conditions. So the MJO is basically this coupling of this large-scale circulation and convection. And unlike other modes like ENSO, which sort of pulse in largely one spot, the MJO is a moving oscillation. It propagates east. And this GIF illustrates that nicely. What's shown here in blue is increased rain, and red here is decreased rain. And this is like relative to a background climatology. And it's been either filtered or processed in some way to pull out the MJO. And you see these signals, right? They form in the Indian Ocean, and then they move to the east. So here's a dry phase moving through the maritime continent and dying out in the Western Pacific. And this oscillation, this formation, propagation, and then decay tends to occur between around 30 and 90 days. I think it's useful not to think of the MJO as like a sine wave. It's really more of sort of an episodic phenomena. So you'll have an MJO event, and then 30 or so days later, you may have another MJO event, but you also may have a few weeks where nothing happens, and then the MJO gets active again. So it has a kind of broad spectral window, but to first order, it oscillates in a sort of sub-seasonal 30 to 90 day space. In contrast to that, the QBO is different in a lot of ways, but the two big differences, I think, or two that I want to highlight, are the QBO happens in a different part of the atmosphere in the tropics, and it happens on much longer timescales. So what the QBO is to first order is it's a reversal in the direction of the zonal mean, zonal wind throughout the whole tropical stratosphere. So this top panel, which is from I think what is still like the QBO review by Mark Baldwin in 2001. It shows a bunch of different sites sampled on the equator, and as a function of height and time, shows the zonal wind. So you see these easterly in blue and westerly in red descending patterns that start in the upper stratosphere and then they descend with time down throughout to around the lower stratosphere. So these easterly, westerly descending, phases are the main signature of the QBO. And the way that one of the ways, probably the most sort of naive and straightforward way to define the QBO is you pick a level that you like, and then you just calculate something like the tropical mean zonal wind at that level. So for example, this bottom panel takes the 50 hectopascal zonal wind averaged in the tropics. So that's around 21 kilometers. And you can see, right, the easterly and westerly transitions. This is a bunch of different reanalysis data sets and some sounding data as well. So we'll talk about the QBO as either being easterly or westerly. And basically, all that means is that the winds are above some threshold when it's westerly or below some threshold when it's easterly. And finally, the quasi-biennial oscillation is called it's quasi-biennial in the sense that its period is around every 2 years. It's something like 20 to 30 months usually. So it's a much longer time scale than the MJO is. So those are the two processes, and we've known about both of them since approximately like the 60s or the 70s for the MJO. But it's really only since 2016 that people started to ask whether they might be connected in some way. And what they found is that there is this surprisingly strong connection. And it's surprising, I guess, in two senses. The strength of it is pretty surprising. So the QBO changes the MJO in a relatively large way. But also, people who have thought about the MJO had not at all been thinking about the stratosphere or stratospheric processes. So it's physically surprising as well. Um, I'll show you a few different sort of plots that show the different observed feature, but I thought I would just start by stating what I think is the central part of this connection. And then I'll also talk in the sort of second half of this intro part about some implications for prediction and predictability. So I think the main result can be stated relatively straightforward. In boreal winter, and I'm taking a broad view of winter here, so let's say from November through March, when the QBO at 50 hectopascal, so when the lower QBO winds are easterly versus when they're westerly, the MJO is stronger, it's more active, and it's more predictable. And I'll show a few different ways of looking at that. So this is from the GRL paper that introduced this link. The right panel is probably the most straightforward way of seeing this link. It's all that's shown is the amplitude of the MJO on the y-axis, measured by some index, so the units aren't particularly intuitive, as a function of where the MJO is in its life cycle. So MJO phase just means, 1 means that the MJO is reigning over the Indian Ocean, 4 means that the rain is over the maritime continent. So what they did is basically they took the all winter average amplitude in black, it's around 1.6, and then they segregated out. If you look at only the easterly QBO or the westerly QBO winters, you make the same amplitude plot, and you see that when the QBO is easterly, the amplitude on average is around 2, and when it's westerly, the average is around 1.3. So it's a very large modulation of the overall strength of the MJO in the wintertime between these two QBO phases. Another way of measuring this, and this is something that I'll come back to this sort of metric in a few points through this talk, is you can take the outgoing long-wave radiation in the tropics, which is just a measure basically for convection. On MJO timescales, it's a fine measure of convection. And what you do is you filter the OLR in space and in time to kind of pull out the MJO signal. So you take a sort of 30 to 60 day bandpass filter of large scale features. And then if you plot the standard deviation, right, that's a measure basically of how much does the convection on this MJO timescale vary. And what you see is, if you just look at all winter, a bullseye in the kind of Indian Ocean maritime continent region where the MJO signal lives. So this measure is basically a way of pulling out, where is the MJO active. And then what Yu and Sun did in their paper is they basically made this same plot, but for easterly and westerly QBO winters. And they took the difference. So these bottom two panels are difference plots relative to the climatology. And what you see is a decrease in the OLR standard deviation, basically a decrease in MJO activity when the QBO is westerly and an increase when the QBO is easterly. And I'm going to use this MJO filtered OLR, this change as a measure later on of the strength of the difference. So if you can keep this this plot in the back of your mind. One more way of looking at this link, I think it was important to kind of drill down on the fact that it's really the strength of convection that's changing. So OLR is a measure kind of cloud top temperature, but a better measure of how strong convection really is actually precipitation, right, on the ground. And so here, what Saku did in this paper in 2017 is they looked at anomalous precipitation. If you just focus on the left column for a second, basically this is just averaging a bunch of different MJO events at different points in its life cycle. So blue is more rain, red is less rain, like the GIF I showed. And here we've averaged a bunch of MJO events that are active over the Indian Ocean. So you see this blue anomaly here, right? This increase in rain. The next panel down is MJO events that are active in the maritime continent. And then the lowest panel is Western Pacific. So you can kind of think of this as like three different sort of points in time, right? You see this eastward movement here. So that's an easterly QBO winters. The right column is the exact same, locations of the MJO, but for westerly QBO winters. So it's the same composite plot, but they're looking at precipitation under a different phase of the QBO. And you see overall, right, just comparing left to right, the anomalies in the left-hand panel are markedly stronger. They're more coherent. Both the active phase is more active. So the blue is darker blue and the red is darker red, indicating that basically, throughout its life cycle, the rain and the convection associated with the MJO is consistently stronger and more coherent when the QBO is easterly than when it's westerly. And there's been a lot of other papers on this MJO-QBO link. They use different data sets. They use different analysis methods. They've sliced and diced this a lot of different ways. And I think a lot of people in the tropical meteorology community are very convinced that this is a real sort of relationship. So I'm going to just touch on three kind of mysterious aspects of this connection. I'm not going to go into too much detail, but I'll just sort of play out what I think are three things that maybe are central to this link and offer or could offer insights into what's going on. So one is something that I've mentioned already, which is the seasonality. So it's only true, this MJO-QBO connection, all of this is only true in extended winter, in roughly November through March. If you look just say in September through November, or if you look in summer, none of these metrics show any strong link. So why is this only happening in winter? And I should say I'm not going to answer these questions. I think if I could, this would be a much more exciting talk. But these are I think the big ones that we ought to be focusing on. The second thing is something that I'm going to call uniqueness. I don't have a plot for this. I'll just say the result. Basically, the MJO, it seems like, is kind of uniquely affected by the QBO. And what I mean by that is if you look at, let's say, the QBO impact on just convection in general. So something like, the mean convection in the tropics from December through February, you don't see anywhere near the strong change that you do when you look specifically at MJO convection. The same is true if you look at the QBO-ENSO relationship. There's not much of a downward impact. If you look at the link between the QBO and other convectively coupled equatorial waves. So if you're not a tropics person, basically these are things that are kind of like the MJO. They're these sort of coupled convective things that propagate. Some of them go east, some of them go west, things like Kelvin waves or Rossby waves. None of those have a strong modulation by the QBO as well. So something about the MJO is really being uniquely modulated by the QBO. And I think that's exciting in particular because it makes us think that maybe whatever is happening is sort of specific to the MJO. And then the last thing I want to talk about, the last kind of component of this link that I think is worth mentioning is that it seems like it's only emerged or only significant in the record after around the 1980s. This slide on the bottom is one way of looking at that from a paper by Phil Klotzbach, and there's a second paper that's just come out that kind of confirms this idea in a different analysis method. So what this plot shows is the correlation between the MJO and the QBO in winter. So here's the 0 line. You can see, at the start of the record, the correlation is basically 0. And the way that this plot works is each point here is actually a 30-year sliding window. So where it says 1920, it's actually data from 1905 to 1935. And then they calculate the correlation between the MJO and the QBO right at that window, and then they slide that window through to the present. So 2000 here is actually 85 to 2015. And two things to point out. One is as you go, farther back in the record, right? We don't have satellite observations prior to the 70s. We don't really have good QBO metrics prior to around the 50s. So you have to reconstruct the MJO and the QBO, and there's uncertainty when you do that, and that's what this spread here is. They have some measure of reconstructing these indices, I think, from sea level pressure data, and they try to make an ensemble. So basically, you might trust this data a little less as you move back in the record. But let's say you do, believe that it's sort of to first order capturing the MJO and the QBO. Then what you see as we go forward in time, right, is that this relationship was basically there was no correlation, and then starting around the 1980s, the correlation starts to sort of drop, and now we're at the point where we see this strong and significant anti-correlation today of around minus 0.6. So something changed or is changing in the climate system that has led to the emergence of this MJO-QBO connection in the past, say, 20 or 30 years. So those three aspects, the seasonality, the uniqueness, and the emergence, I think are three of the components of this connection that are most interesting to me, and that I think any theory of the MJO-QBO link should be able to explain those three aspects. I'm just going to really quickly touch on another aspect of this problem. This could be a whole other talk into itself, but for time, I'm going to sort of stay focused and get to the modeling work that we've done. But in addition to the sort of science question here, which is, we have these two modes and they're linked in this interesting way. And if you study the MJO, this is exciting. Theoretically, there's also an aspect that I think is more closely linked to, to people and to impacts. And that's that the QBO changes how predictable the MJO is, and also how predictable other sort of S2S teleconnections are. So this plot here is from a paper by Lim et al. That came out last year. And if you just look for a moment at the black bars, let's just say the black bar in this leftmost column, what this shows is the skill that a bunch of different forecast models have at predicting the MJO. So these are not GCMs, right? These are forecast models that are part of the S2S database. They're basically optimized for subseasonal predictability, and a lot of them have spent a lot of time working on the MJO. And so you see the different shades of black or blue or red are just different measures of skill. But if we just take the sort of most relaxed measure, the way to read this plot is, right, the Bohm model basically has MJO prediction skill in winter out to around 26 days. You can see the ECMWF model has prediction skill out to around 35 days, and so on across these 10 or so models. So then if you take these same collections of forecasts during winter, and you look at the easterly QBO versus the westerly QBO forecasts, that's what's shown in blue and red respectively. And what you see is across all of these models, the MJO forecasts are more skillful when the QBO is easterly than when it's westerly. And the change is about 1 week, which when you think about the fact that, just looking here, we only really have skill out to around, let's say, 2 to sort of 5 weeks is the range. A change of 1 week is pretty substantial. So the MJO is much more predictable when the QBO is easterly than when it's westerly. And work has shown that it is not just the fact that the MJO is stronger that is leading to this predictability change. There's something, we don't understand what, but there's something more sort of fundamental that makes the MJO behave differently and become more predictable. So again, I won't go into all of the sort of implications of this, but basically this means that this problem, this connection, has applicability, I think, to a lot of S2S prediction questions and could be used to leverage, make better forecasts of opportunity or something like that moving forward. So I think hopefully I have convinced you that that this link is real and that it matters both from a sort of theoretical, we want to understand the tropics, but also from a sort of practical, we want to be able to make good predictions. And so now I'm going to talk more about the mechanisms or the sort of the proposed mechanisms that might explain this link, and then talk about the sort of work that we have done at GISS, trying to use models to understand this connection and the walls that we've hit up against, the struggle that we've been having. So just to start, I think it's worth recognizing that this is a tricky task to ask a model to do, because I think up until relatively recently, if you even could find one model that had a good MJO and a good QBO, that was considered a challenge. That's changed recently, but if you look at, for example, like the CMIP3 or the CMIP4 models, you'd be really hard pressed to find one that had a good MJO and a good QBO. So finding good models to look at this problem is still difficult, but is now at least tractable. And I just wanted to highlight one half of the challenge, which is the QBO. So I've taken different snapshots of the performance of different CMIP6 models at representing the QBO. So this is from a paper by Yaga Richter from this year, where she looked at something like 30 different CMIP6 models and diagnosed the QBO. And I've cherry picked 3 here just to make a point. So the top left is observations. So what you see here is this is the zonal wind as a function of height and time from 79 through, I think, like 2018. So in observations, you see, right, this is the descending easterly and westerly QBO regimes, right? This is similar to the plot that I showed in the intro. And then I've chosen 3 models basically at random just to show sort of 3 different model behaviors, even in the most current generation of CMIP6 class models. So I'm showing the MyROC model here. I'll show a version of the GISS model later that also looks pretty good. Some models, have what looks, if you're not a QBO expert, it looks like a very good QBO. If you're an expert, you can see differences and they're important, but to first order, it has this quasi-biennial oscillating descending wind pattern. So we can get the QBO and we can tune things like the period and the amplitude. We know what knobs to turn in models to get it. But there are still models which have no QBO. So the bottom left is an example of that. I'll show another example of a GISS model with no QBO. Typically, those models are lower vertical resolution, and the modeling center has just, for whatever reason, a lot of modeling centers don't really care about the QBO, and so they haven't put the resources in, or maybe it's something about this particular model. But here you see there's sort of weak westerlies or easterlies in the stratosphere. So there's plenty of models still with no QBO. And then there are models that have something that looks, it's like a quasi-biennial oscillation, right? This bottom right model certainly does not look that much like the real world, but it also doesn't look awful. It has these sort of pathological periods where these westerlies stick around. So you can get things that are sort of quasi-biennial oscillation like, but there's still quite a bit of a diversity of performance in the model. So, okay, fine. We have models which do and which don't have these oscillations. In the models that do, how do they do? And I think I've kind of alluded already to the fact that basically no climate models show a strong or a significant MJO-QBO connection. I saw there was a question. So Claire, if you want to.
Yeah, great. Costas has a question. Costas, feel free to.
Yeah. So can I ask, is there a pattern for the models that don't have a QBO? Does that, don't having a QBO means that they have either mostly easterlies or mostly westerlies, or some very incorrect seasonality of easterlies and westerlies? Is there a pattern, or it is all over the place?
I think that's a good question, and I don't know off of hand. I think that generally models tend to have sort of very weak, like you can see here, we have very weak westerlies. I think the GISS model, which I'll show, has sort of weak easterlies. But I think in general, when a model doesn't have a QBO, usually it basically just has very weak winds in the stratosphere. So these sort of like very strange oscillations, they don't really occur. You kind of have to have put in at least some kind of a QBO to get these strange oscillations. I would say the 2 ingredients. This is sort of an answer. The 2 ingredients to have a good QBO, very broadly speaking, or you have to have relatively high vertical resolution, and you have to have a convective gravity wave scheme that is sort of state of the art enough to sort of send the right gravity wave fluxes up into the stratosphere. And then once you have those two things, you can kind of tune the gravity wave scheme to sort of get the QBO to work out. But I don't know if there is kind of, a consistent bias in the no QBO models. That's a good question.
Thanks.
For sure. Okay, so I was just going to make the quick point that basically of those models that do have a good MJO and QBO, none of them show a strong connection like that observed. So this is from a paper by Jaime Kim, where she looked at the CMIP6 models that had, by the sort of measures they define in this paper, that had a good MJO and a good QBO. And they looked at the link across all of them. So the way to read this plot is the y-axis here is kind of a measure of the MJO-QBO link. So what this is it's the change in the standard deviation of OLR averaged over the warm pool. So it's similar to that plot I showed before where you take, the filtered MJO and you plot the kind of the bulls. Gavin, I'll show the GISS E2.2 in a second. I think that this paper came out before the GISS model went into the CMIP6, but yeah. So here basically, right, what the positive y-axis means is a stronger or more active MJO when the QBO is easterly. And the units are a little hard to get an intuition for, but basically, right, you can see like a three sort of sigma OLR change in observations. Then each of these black dots is an ensemble member from one of these climate models. So first off, you'll notice that none of the black dots come anywhere near this observed change. So what that tells you is none of the individual ensemble members have a strong MJO-QBO connection like that observed. And furthermore, if you look, within each particular model, basically the ensembles tend to be clustered around 0. And these gray bars are some measure in this paper of basically what you would get from just sort of sampling noise. So looking at just the MJO change in years where there basically is no QBO or the QBO is weak.
Zane,
So
I have a question.
Yeah, go ahead, Clara.
So given the slide that you had showed at the beginning about the kind of evolving nature of the relationship, are these PI controls or is this historical? And did they look at different periods over the historical range?
Yeah, I think that these are all historical, and I don't think they just looked at the 79 to 2017 or something.
Great, thanks.
They looked at the period that is analogous to this observed, so you're comparing apples to apples in the sense that it's the observed change from 79 through 2015 or whatever, and then it's the model over that same period of time.
Thanks.
As far as I know, no one has looked at like an RCP 8.5 scenario, and if you, I don't know, naively you might think that if that MJO-QBO curve continues to go down, maybe it would be stronger in the future, but I don't want to speculate too much on that. So all the work has been basically on kind of historical runs. So none of these climate models are showing a significant MJO-QBO connection. And one question is sort of, right, the big question, I guess, is why? And I'll talk about sort of one proposed mechanism and how it relates to climate models. So first, to just take a step back and talk about this mechanism, the idea basically is that one way that MJO-QBO relationship might work is that QBO changes to temperatures in the upper part of the troposphere might affect the MJO. So this plot on the left is the QBO east minus QBO west temperature change. So basically, if you think about, right, I had that time series of the QBO at 50 hectopascals. You just take the easterly periods and the westerly periods and you subtract the temperatures, you get a plot that looks like this. So I want to draw your attention to basically on the equator, so this is latitude height, on the equator in the lower part of the stratosphere, there's these cold anomalies that are associated with the QBO easterly phase. And in the westerly phase, you get the converse of this panel, you get warm anomalies in the lower part of the stratosphere, and they reach down to kind of around the tropopause. So the idea is, and it's a little hand-wavy, but the idea is that maybe these cold temperature anomalies destabilize the upper atmosphere. So you can kind of imagine, like very naively, if you make it colder and you have a partial that's ascending, it can sort of continue to ascend into a colder tropopause, and the convection tends to be deeper and more sort of vigorous in the vertical. There's sort of more nuanced takes that look at, the MJO also has a kind of cold temperature signal kind of around this same point. And so maybe there's some sort of interaction with the QBO and the MJO temperature signals. There's a feedback. And there's been proposed hypotheses for how this temperature mechanism might relate to the seasonality and the uniqueness and the emergence of those three theories. So I would say this temperature anomaly, whether or not it's right, it's the one that has received the most attention in the literature to date. And so when we look at how models do at simulating these temperature anomalies, in general, even the models with a good QBO do somewhat poorly. So what I'm plotting here is again the change in QBO east minus QBO west temperatures. It's a function of height. And here I've just averaged over 10 north to 10 south, or Jaime's averaged over 10 north to 10 south. So instead of a latitude height plot, it's just a height plot. So you see, right, again, in observations, when the QBO is easterly versus westerly, you get like a 3-degree change. And it goes down to around 100 hectopascals. Already you'll see, right, that these changes are pretty small. And in particular, they're pretty small around the tropopause. So that should maybe give you some pause. But what you also see is all of these colored lines, which are the temperature anomalies in a bunch of different CMIP6 models. With one exception, they all lie to the right of the observed. So in other words, even the CMIP6 models that have a good QBO systematically underestimate the strength of these QBO temperature anomalies. The one model that gets it kind of right is E3SM, and that's one of the models where if you actually look at the evolution of the QBO, it looks a little funky in this model. Like the westerly phase tends to be way too strong. So even though this is getting the temperature signals right, there's sort of other QBO biases in this one outlier that maybe suggest that kind of might suggest why it doesn't get the right relationship. So we wanted to basically look at, in particular, this hypothesis that QBO biases and temperature biases, might be the reason why the MJO-QBO link is missed in models. And if we can show that's the case, it's good in two senses. One, we know now how to put it into the model, and two, it gives us sort of some hope that this mechanism is maybe correct. So to start, we just looked at the model that Gab and I saw asked in the chat about, which is the GISS model E2.2. So this is a 102 level vertical resolution model, and it has a free running QBO. So this model, naively is basically similar to the ones that I just showed in the sense that the QBO is kind of whatever the model is capable of producing on its own. And you can see, right, here's the QBO zonal wind on the top and the model QBO wind on the bottom. And this is, as I think I alluded to, this is one of those models that, if you're not an expert, it has a pretty good QBO. Actually, even if you are an expert, it still has a pretty good QBO. And it gets things like, the sort of the stalling of the westerly phase tends to sort of stick around for a long time here in the lower stratosphere, and it captures that. The amplitude looks quite good. So we started off by looking at this model and looking at the MJO-QBO link, and we found, consistent with the Kim et al. Results, that this model has no MJO-QBO connection. I'm not going to get into the details of that because it's not too different from the sort of published literature. Basically, this version of the model with a free running QBO has no link. And when you look at these temperature signals, the GISS model, 102 level model, suffers from the same biases that other state-of-the-art CMIP6 models suffer from. So you see, this is a plot of the observed change in the QBO temperatures. You see this cold anomaly in the lower part of the stratosphere here from around 50 to 100 hectopascals. And then you see in the models, a much too weak signal in this lower region. The difference is on the right, and it's a little here. Warm basically is consistent with just less variability overall. So it's not cold enough in the easterly phase, and it's not warm enough in the westerly phase.
Zane?
Yeah, go ahead, Claire.
So there was a question in the chat about whether this was using the non-interactive or the interactive composition. So this is the non-interactive, correct?
Yeah.
Do you want to maybe comment on because you looked at some of the OMA runs?
Yeah. So the question basically is, is the chemistry in these runs interactive or not? Meaning, is the I guess ozone. I don't know too much about this, but my sense is ozone is the kind of major player in this. The answer, yeah, as Clara says, this is not interactive. If you do look at the versions of this model with interactive ozone, the temperature anomalies are quite a bit better, and that we understand why that is. There's sort of ozone temperature feedbacks that we think we understand that sort of explain why, when you put in interactive chemistry, these temperature biases are not as bad. But we still found no MJO-QBO link in that version of the model. So interactive versus non-interactive doesn't seem to make a huge difference for the connection. And I'll talk maybe about why that is if I remember at the end. But yeah, that's a good question. So what we did do is we decided
Ask
to look at,
something.
yeah, go ahead.
So, the E2.2 model has a cold bias at surface. Isn't that affecting convection and then so suppressing convection essentially, and then maybe affecting MJO in ways that break
Yes,
some link?
that's exactly right. So there's there's two reasons that we didn't. So in addition to the fact that the E2.2 model has a sort of, it's not capturing those temperature signals, it also has a poorer MJO than the version I'm about to talk about. So this plot, which I'll show another example of later on, this is a regression plot of OLR associated with the MJO. So basically what you see, it's like you regress the OLR, in this case against a region in the Indian Ocean. Observations is on the left, and then an AMIP and a coupled version of the E2.2 model are on the right. And what you see is that the propagation is really not well captured at all in this E2.2 model. The strength of the MJO tends to be too weak. We also looked at that. So yes, in addition to having biases with the QBO, this model also has a poor MJO, or a less good MJO than the version I'm about to talk about. And this is another reason why in those interactive chemistry runs, even though the temperature anomalies were better, they still had this sort of poor MJO. So that's another reason why we maybe don't like this E2.2 model so much, is that that the MJO is not as well represented. That's a great thing to stress. So fortunately for us, there's a model E2.1 which does have a very good MJO. So basically, right, we decided, okay, we've looked at E2.2 and there's nothing there. What can we do with E2.1? So the first, if you know this model, the first problem is that E2.1, as it's normally run, has no QBO. So right off the bat, we have to do something to sort of set up the problem, right? You can't look at this link in a model with no QBO. Here I'm showing a control run, and what you see is sort of weak easterlies throughout the stratosphere, right? There's no descending oscillation. But this model has a very good MJO. So these are regression plots like the one I just showed. But now for the E2.1 model, and you can ignore the bottom right panel. So you see in particular, the bottom left is the coupled version of E2.1, run in just standard control mode, so with no QBO. And this model does a really nice job relative to its sort of peers of propagating the MJO. The correlation looks reasonably good. This is a composite around the maritime continent, which is where models tend to do the worst. So I'm kind of asking the model, a hard question, and you can see, again, this coupled version looks relatively close to the observed. And other measures of the MJO, like its amplitude and its seasonal cycle, look especially good in the coupled version of E2.1. The AMIP version is a little bit worse. So I'm going to show results from the AMIP version, but really we focused on the coupled version because it had a good MJO. So we have a model with a good MJO, and we know that stratospheric biases might be important for this problem. So what we did basically is we just decided to nudge or to relax the stratosphere to basically take the E2.1 version of the model and put the QBO in, just force the QBO via nudging. And the way that we did that is basically at each time step, right, the model's stratospheric, zonal, and meridional wind, so we're just nudging the winds, were relaxed towards the Mira 2 values on some time scale tau. So basically, naively, what you do when you do this is you just take the difference between, right, the model and the observed, and then you add a tendency term that sort of pushes the model towards the reanalysis value. And this timescale tau controls how closely does the model match the reanalysis. So if you do something like 30 minutes, it's really locking the model into the observed, or to the reanalysis, I should say. And if you do a longer time scale, it lets the model sort of evolve on its own more. So we did a time scale of 12 hours, and importantly, we only nudged above 100 hectopascals. And the reason is that we wanted the MJO to be able to do its thing and freely respond. So the idea is that we're nudging the stratosphere, but we're not touching the troposphere, and we're letting the troposphere evolve in some way that hopefully captures the MJO-QBO link. The other thing I'll point out, which is a little bit technical, is the way that we implemented the nudging in the runs that I'm going to talk about is we, instead of nudging at each grid point, so instead of saying, at this latitude and longitude point, the observations in the model have to match, we nudged the zonal mean of the model towards the zonal mean of the observations. So it means that basically the model is allowed to disagree with the reanalysis zonally, but the overall zonal flow is confined. And the reason that we do that is basically it allows sort of more of the model physics and the waves that propagate up. It constrains them less, it damps them less. But ultimately, that's not going to. We sort of did a bunch of experiments looking at different settings, and it's not going to matter too much. It's more of a technical note. So when we do this nudging, after a little bit of elbow grease, we had to sort of mess with the vertical coordinates to get it to look good. Ultimately, this model does a very nice job of representing the QBO when you force it, which is maybe not a huge surprise. In general, nudging experiments like this are not super new, and they've been relatively tried and tested. So what you see here, right, is this is the observations. The middle is the panel I showed before, the control run. And then here's the coupled version with the nudging, and you can see it's night and day in the stratosphere. We're representing the QBO reasonably well. There's still some biases, and this paper is under review now, and Claire and I are just trying to sort of really understand the sort of fine details of this. But again, to first order, we're getting the QBO signals, very, very well represented. And in particular, even though we're not nudging the temperature, and this is something I want to stress, right? We're only nudging the wind. The model has these same QBO temperature signals, and they're no longer too weak. So this is a similar plot to the one I've shown, right? This is the QBO east minus west temperature anomalies, and you can see it in the lower stratosphere. That is, they're very well represented. If anything, the model is actually a little stronger than the observed, but there's some reason to think that that's not a bad thing. If we're forcing the model a little too strongly, if anything, we might expect a sort of stronger response. There are still temperature biases at upper levels, but I haven't really worried about those or thought about them too much, because really, this mechanism kind of is all about these lower stratospheric temperature signals. So, okay, we've got this model. It has low temperature bias. We're getting these QBO temperatures. The MJO is relatively good. And then we go in and we look, and unfortunately, basically, across many ensemble members, we found there was no clear MJO-QBO link. So ultimately, what we did is we ran the model, over the historical period from 1980 through 2017. We did 11 coupled model ensemble runs and 5 AMIP model ensemble runs. So we really did a lot of different, simulations. And the QBO each time is nudged identically. So the only variability is coming from the troposphere. And what you see is by 2 different measures, the model is not as strong as the observations. So this left-hand column is that MJO-QBO activity, the change in the OLR field. You see the observations is this black X up here at around 2, and the model is really clustered around 0, in particular the AMIP version, but the coupled version as well. You can see there are some points where, and it's funny, this point here that looks closest to the observations was the first ensemble member we did, so we got all excited. But if you look at other measures, there's really we've convinced ourselves that there's really no strong link across this ensemble. The right-hand column is just a different metric. It's the correlation of the MJO and the QBO. So you see the observations is down here at a strong, significant anti-correlation, whereas the AMIP and the coupled runs are clustered around 0, or the AMIP runs actually have the sort of opposite sign, which is difficult to understand. So
I'm sorry, I might have missed it. Have you evaluated the MJO in this new model configuration?
In the nudged, yes. So I sort of glossed over it, but right, I mentioned that in E2.1, the MJO is very good. And we did a few things to just check that when you nudge, the overall MJO doesn't change. So you see in the bottom right, the coupled version with the nudged MJO. And it looks very similar. The differences you see if you look across different ensemble members, like it's just consistent with the internal variability. So by nudging the stratosphere, we haven't fundamentally altered, the MJO hasn't suddenly gone haywire. So we did, yeah, we went ahead and looked at that just to make sure that the overall behavior of the MJO was similar between the control and the coupled. That's a good question. So okay, the main takeaway then, and I'll talk about some other sort of next steps. The big thing that we did, right, is we tried to impose the QBO in a model which has a relatively state-of-the-art MJO, and we reduced a lot of these biases. There are still some biases in the model. So, for example, the temperature at 100 hectopascals is still about 1 degree warmer in the model than observations. So we haven't totally reduced the biases. But we've gone a long way towards getting the QBO temperature signals right, better than any of these free-running models, and that doesn't resolve issues simulating the MJO-QBO link. We did a ton of different sensitivity tests too. We looked at the way we implement the nudging. We looked at the where in the vertical we apply the nudging. We looked at the nudging time scale. We even did some where we nudged to a QBO that was 50% stronger to really just force the model, and in none of those simulations do we see something like the observed. And so I think it's still an open question then, why are models failing to get this connection? And I don't think that it's just the case that it's all about these temperature signals. I think that the story is going to have to be more complicated, is what our work shows. I'll just give some sort of next steps on further interpretation. So it may be one thing that we looked a little at is that there are MJO biases that are a little sort of subtler, that are not the sort of typical things that people look at, that may be important. So for example, what I'm showing here is a plot of the MJO in the upper part of the troposphere. So this panel on the left, the sort of top portion of this panel, is height and longitude. So it's like a cut along the equator of the MJO, starting at 500 hectopascals. And this is observations on the left, and this is the coupled model on the right. And the shading here is temperatures, and the arrows are the zonal and vertical wind. So what you see is, again, without going into the sort of details of this regression too much, the observations have a very strong and sort of coherent ascent, and then also a strong descent. And there's this sort of strong warm temperature anomaly in the upper part of the troposphere. And the model has sort of the same basic picture, but it's, the ascent is quite a bit weaker, the temperature anomaly is quite a bit weaker, and the sort of vertical tilt of the model, if you look at this, these sort of signals in the upper part of the troposphere here, the model has a sort of more tilted structure, which is sort of consistent with something like a Kelvin wave and not with the MJO. So it may be basically that there are still biases in the MJO, in regions like the upper troposphere, that we need to try to think more about how can we improve them. And this is really a hard question. We can't do something like a nudging, of the MJO, that there's not really a way to set that up in a way that makes sense. But can we somehow sort of try to look as a next step at addressing these MJO biases more and trying to understand, where they come from and resolve them. Another thing that we're doing is we're extending this work to 3 other models. So Claire and I have been working with folks at NCAR, E3SM, and GFDL to basically repeat this nudging experiment, so you can see different nudging profiles from the 4 different models. I think, again, our initial work has shown that, at least in the GISS model, this nudging is not the sort of silver bullet for this problem, but we wanted to look, at other models and try to understand, whether this was a problem across all of these models, and also to sort of build a community of people that were interested in this problem, and could maybe work going forward. And I'll just, it's always a good idea to kiss up to the home crowd. This is those MJO regression plots that I showed before in observations, and then for the 4 different models. And you can see that the coupled version of this GISS model has a really nice MJO. The propagation is much better than these other three versions. So again, that's a sort of reason why we might like this model in particular. And I think if you're an MJO person, the CMIP6 version of this coupled model looks pretty good, though again, there are biases in the upper part of the troposphere that might matter. I'll kind of skim over this slide. Some other possible ideas, right? It may be that really we just still don't understand the physics or the right mechanism, and the experiments we're designing just aren't the sort of right experiments because we haven't sort of thought about this the right way. So you could imagine things like wave propagation could be important, things that have nothing to do with QBO temperature signals. And I think that's a place where, if you know about the stratosphere, if you're a sort of theoretically minded person, can you come up with other hypotheses that we could test about how this MJO-QBO connection might work? It's also possible that resolution might play a role. There's been a couple papers, one that I wrote last year and another by Bach from this year, that looked at cloud resolving models and showed that there's still too weak of a link in cloud resolving models, but in general, there's maybe more of an MJO-QBO link there. And so, it may be that you just need high resolution convective representation to capture this. And if that's the case, it's a little hard to see, GCMs as the way to think about this problem. But I think that's an area where we need to do more work. So I'll leave you with this slide again, right? We have these two oscillations, the MJO and the QBO. Spent a lot of time thinking about them, and they're linked in this very strong way. I hope I've convinced you of that. And the problem that is still open is, why are they linked, and what's going on in models that explains this failure. And I think resolving this is really important. I mean, I'm biased because this is what I've spent time doing, but I think there's a lot of directions that this work could go. I think the one sort of exciting aspect is, could this QBO impact be the kind of link into understanding the MJO in general? So we still don't have a great theory of the MJO, but we've found a process that seems to modulate the MJO and uniquely the MJO. So, maybe this will ultimately lead to a better understanding of the Madden-Julian oscillation itself. As I sort of alluded to, there's lots of implications for S2S predictability. People have started looking at, predictability of atmospheric rivers that affect the West Coast, and they found that if you take the QBO and the MJO both into account, your predictions are better. So, can we leverage this link to improve predictions? And finally, I think it's a little worrying that there's this strong observed link that we're missing in models. And so, can we understand what it is that we might be missing? Is this process, whatever it is that's operating in the real world, is that important for other modes of variability? And if we can figure this problem out, do our tropics look better in models? So I think it's a great question, and there's a lot of different ways one can sort of come at it. So I'd be eager to talk to anyone. So I'll just leave up. There's my contact info, some stuff I've worked on, some people I've worked with, and especially these days, I would definitely love to, just to talk to people about this work or other work. So thanks very much, and take a little time for questions.
Great. Thanks so much, Zane. That was a really wonderful overview of the work that you've been doing, some of the work that you've been doing. We had a few more questions that were raised in the chat.
Yeah,
I'm going to go
great.
back to one that Gavin mentioned. This was about, it's a little bit, I kind of asked something somewhat related, which was about if it is true that the QBO-MJO connection has been increasing over time, this suggests a forced response. Are the runs we're doing with modern or PI forcings? So don't know if you want to.
So these runs have historical forcing. So to that extent, I think we trust that that's less of an issue. But I do think you're right that it does suggest some kind of a forced response. In the Klotzbach et al. Paper, they talk about the warming of the troposphere and the cooling of the stratosphere from both ozone and CO2 as one possible reason. So you could imagine maybe doing something like a 4 times CO2 run or mess with the ozone to kind of exacerbate that difference even more. That's maybe that would be an interesting experiment to do. But I did look too at just the last 20 years of the run as opposed to the full 30. Just focusing on the most recent period, and it doesn't seem to matter much. So I don't think that the issue here is that we're missing some kind of forcing. That's a guess, but
great. And so then next we have a question from David. David's also on the line, so David, you can unmute yourself. But David asks, which tropical waves is the MJO associated with that could influence the QBO?
Yeah, that's a great question. So David, I don't know if I have a backup slide for that. Basically what David is thinking, I guess you're thinking about an upward impact, right? You're thinking about everything that I talked about today is, the QBO impacts the MJO. But if it's the opposite, right, it may be that when the MJO is stronger, it excites different waves that matter. So the MJO is associated in particular with a Kelvin wave. So there's a strong Kelvin wave response, and you can't really see it here. Basically, the MJO tends to radiate a Kelvin wave off to the east. So you have the active convection, and then that sort of lets Kelvin waves propagate upward. I think there's two sort of tricky things about that. One is, even if the MJO is changing these sort of propagating waves, it's still not clear why the MJO has a quasi-biennial. Like, the MJO would then have to be stronger on its own for some other reason about every 2 years. So it's a little tricky to understand, where would if it's a forcing from the MJO, where is that interannual period coming from? But I think it would be great to just look at, in QBO East versus QBO West, do you see differences in the wave spectrum coming up, out of the troposphere? And if you do, can you associate those differences with the MJO? I don't think anyone has done that yet.
Zane, there's a whole history now of people looking in the stratosphere at stratospheric waves. And
Sure.
for example, above the levels we're discussing here, the Kelvin waves are found to be, in most models, are found to be too weak. And an example of that is the semi-annual west winds in the upper stratosphere in all models are too weak.
It's like the SAO.
Yeah. And people have actually found that Kelvin waves seem to be more associated with variability in precipitation. So the convection schemes that give you a lot of variability, like moist adiabatic adjustment, seem to do a much better job of generating the proper Kelvin waves.
That's interesting.
The question is, why can't models generate, and now we're not only talking about the unresolvable Kelvin waves, we're talking about resolvable ones too. Why can't models generate the proper Kelvin waves when they have a realistic convection scheme?
Sure.
So I don't know. Yeah, I mean, the time scales are very different, but maybe there's something about the inability to generate waves that we know are associated with the QBO and also convection that.
Sure. Yeah, you could do some sort of simple, you could test those kinds of, you could do even like in a dry model, where you just impose some sort of a heating. You could do those kinds of experiments. So I think that's a great topic, and that's something that I know like Adam has been thinking more about too, is can we come up with modeling experiments to test that hypothesis? So it's a great point.
Great, thanks, David. And then we have a question from Kevin Del Santa asking about have you done any zonally asymmetric nudging, and might that play some kind of role into this?
Yes. So I guess by zonally so we have done the nudging where you nudge none of these slides are really that good. Basically, we have done the nudging where instead of nudging the zonal mean, you nudge at each grid point. So these are a little overwhelming, but basically these are plots that show the MJO amplitude in QBO East in red and West in blue. So like here's the observations you see, right? The red line is always above the blue line, so that in observations, right, the QBO, the MJO is stronger in the easterly phase. So these top right two panels are from a coupled and an AMIP run, where instead of nudging the zonal mean, we nudged, at each grid point. So there the model captures the zonal asymmetries that are there in the observations, and there's no strong link. We haven't done any more like idealized experiments, like you could imagine nudging to one profile over the maritime continent and a different profile somewhere else, for some reason. We haven't done anything like that. So I hope that answers the question.
Great. So unless somebody else has another question, someone does, they can either just unmute themselves right now. So I think at this point, I thought I saw some. I think at this point, I just want to thank you again, Zane, for giving a really, really great talk.
Thanks.
Thanks so much, and thanks to everyone for joining. Thanks a lot, and have a great week, everyone.
Yeah. Great. It was great to sort of see you all. And yeah, please feel free to reach out if you have any questions or anything. Thanks a lot.
Thanks, Zane.
Mm-hmm.
Bye, everyone.
Bye.
Bye.
Bye, thanks.